Hey, it's Mr. Lum again, and we're going to be continuing on with some Science 9 stuff, and we're going to be talking about atoms. And yeah, so anyways, so as we talked about before, the atom is the smallest piece of an element that still has the properties of an element. Once you start removing some of those other pieces like protons and neutrons and electrons, it no longer becomes an atom. It becomes something a little bit different. So in order to maintain the same properties that the element has, like melting point and boiling point and all that kind of stuff, the smallest piece of an element is an atom. Now, there are smaller things than atoms, and there are the portions that make up an atom. And so the things that make up an atom are protons, neutrons, and electrons. Protons are positively charged subatomic particles. So protons are positive, neutrons have no charge, they're neutral, and electrons are negatively charged. Now, the protons and the neutrons are located here in the nucleus, and the electrons are orbiting the outside. So here's the nucleus of the atom right here. Now, we have seen this picture many times in grade 8, many times in grade 9. The next big question is like, how did we come to know this stuff? How did we come to know that protons and neutrons are located in the center and electrons are orbiting the outside? So we're going to go through a little bit of the history of how we discovered the atom. So the first major guy that kind of like did some stuff with the atom is John Dalton. And he came up and said that, hey, all matter is made up of small particles called atoms. He said that all atoms of the same element are identical. So all iron atoms look like this. All oxygen atoms look like this. And he also said that atoms cannot be created and atoms cannot be destroyed. Okay? Now, they can combine, right? Iron and oxygen can combine, but it's still just oxygen is oxygen, iron is iron. Okay? And John Dalton also came up with a lot of other things. Like he came up with all of our conservation laws, and you may have heard of these things. Like the one that we have written here is the conservation law of mass or matter, and which says matter cannot be created nor destroyed. He also came up with conservation law of energy. Energy cannot be created or destroyed. It can only be changed, and a whole bunch of others. Law of conservation of electrical charge. Electrical charge cannot change. It can only be moved and switched and altered, but you cannot just have negative charges come out without positives being arisen somewhere else. So he came up with a lot of different conservation laws. But he had a very basic understanding of what atoms look like. And he was kind of like, they're indivisible. That means they can't get any smaller than that without still being iron, for example. And then there was another guy, and his name was J.J. Thomson. And he had the first diagram of an atom. And this was his diagram of the atom. He said that an atom is a spherical kind of thing, and he says that it's all roughly positive, an atom, and it has like these negative little chunks inside of it. And these negative chunks are of course electrons. And he says the electrons just kind of are just like placed in random kind of spots throughout it. He called it the plum pudding model. And because when the time of J.J. Thomson, plum pudding was the dessert of choice. And what plum pudding is, it's like pudding with kind of like raisins thrown into it, right? So if you can imagine, like this is like a bowl of pudding, and each one of these electrons is like a raisin somewhere found in the pudding, right? And just kind of evenly distributed it. Now, I think if J.J. Thomson came up with this picture now, he'd probably call it like the chocolate chip cookie model, where, you know, here's our chocolate chip cookie, right? And then we have these chocolate chips that are kind of placed wherever, distributed throughout the cookie, some deeper, some shallower, and some in all these different places. But the big thing is that he thought like the cookie dough was lightly positive, with like these chocolate chips being these negative chunks, or those were the electrons. Now, as we know today, this plum pudding model isn't correct, but that came for a guy named Ernest Rutherford, and he made this experiment, which is now called the gold foil experiment. And he made this experiment to test to see if the plum pudding model is true, if these negative chunks were just lightly scattered everywhere, and those negative electrons are lightly scattered everywhere, and the whole atom is just lightly positive throughout. So he made this experiment, and what he did was he got what's called an alpha particle emitter. For all intents and purposes, you can think of it as a gun that shoots these radioactive alpha particles. Okay, so it's a gun that shoots radioactive alpha particles. Now, he shot it at a piece of gold foil. The reason why he chose gold is because gold has a really unique property where you can hammer gold into a very, very thin sheet of gold. So it's unbelievably thin, just very, very, very thin. And so that's why he chose gold, is because you can just make it so thin. And then he put this big, large zinc sulfide sheet all around the gold foil. It actually kind of went like, it just wasn't like in a two-dimensional, it also like kind of went up over top of it and underneath as well, but it went everywhere. Okay, and then he shot these radioactive particles through his alpha gun, and he shot these radioactive particles at the gold foil. Okay, and then he looked at what happened. So we're going to take a look at how that experiment discovered the proton. So again, here is my gold foil, this thing right here. Here's his alpha particle gun. Okay, so it's it just shoots alpha particles. Alpha particles are radioactive helium particles. But yeah, so he turned on his alpha gun and shot it right at the gold foil, and it shot just like these. So here these little green balls are shooting out of it, and this was expected. Okay, oh, and then we had this. So what we had right here is that what he expected is that this gold foil is so thin, he expected all of those alpha particles to go through. Okay, and so he had expected. And if you saw one of those alpha particles, they hit and it went deflected right like this, and it went over here. Okay, that wasn't really expected, and he was like, that's kind of weird. But this one was not expected at all. One of the alpha particles bounced off of the gold foil, and he looked at it. He shot it with thousands and thousands of alpha particles, and probably somewhere around 99% of the alpha particles landed somewhere around here. Okay, and maybe the odd alpha particle, maybe 0.75% landed way out here, and just like 1 out of every 1,000 or 1 out of every 2,000 actually bounced off of the gold foil and went backwards way over here. Now, how did he know these alpha particles bounced off? Is because of that zinc sulfide screen. every time a zinc sulfide screen gets hit with an alpha particle, it lights up and it emits some light. Okay, and his big question is like, hey, why are these things bouncing off here? Because if it was true and these were plum pudding model, an alpha particle should be able to just rip through. There's nothing in the plum pudding model that would stop an alpha particle. And so he said that plum pudding model must not be true. There must be something inside of an atom that is hard and dense that would that an alpha particle could bounce off of. And so he came up with this. He said that a gold particle has all of its positives in the center, and the electrons are just floating around the outside. And so, because he said, according to the plum pudding model, there is nothing hard for the radioactive particles to bounce off of. So Rutherford said there must be something hard and dense in the center, and he proposed the proton. And so what he said was the proton is really, really small and doesn't occupy a very much space. And so, but it's very, very dense, and it's only located in the very center. It only occupies less than 1% of the volume of the atom. And the electrons are just flying around the outside. The electrons are pretty insignificant. And so there's all this empty space right through here and right through here and right through here for alpha particles to go through. Just like these, okay? So much empty space for the alpha particles to go through. But occasionally, an alpha particle will hit it and get deflected and go down here. And very occasionally, an alpha particle will hit it dead on and bounce backwards. And so this experiment proved that there was something hard and dense inside of it, and he said that hard, dense thing that was positively charged was called a proton. And so this is how Ernest Rutherford discovered the proton, is through this gold foil experiment. Now, this is a little bit weird, but like Ernest Rutherford also came across another problem, and his other problem was like they didn't know about a neutron. And I'd like you to write this down because I think this is a pretty cool discovery. But there was, Ernest Rutherford came across the problem. He said like, okay, this is how many protons are in gold, but it doesn't account for the mass of gold. He just couldn't figure out why gold was so heavy, because he calculated how many protons were in there and all that kind of stuff, and he couldn't figure out what was there. And so he had a bit of a problem, and because at this point they never discovered the neutron. And it wasn't until a guy named Chadwick, that was his last name, Chadwick came along, and he wasn't really like, he was a science person, but he said that, hey, there must be also another thing in the nucleus of an atom next to the proton. And he said, it doesn't have a charge. It's also probably just as heavy as a proton, maybe even a little bit heavier. And he said it doesn't have a charge, and he called it a neutron. How did Chadwick discover this? Is purely based on mathematics. All he did was say like, hey, the mass of the atom isn't adding up to how many protons are there. So mathematically, there must be something that is roughly the same size as a proton, and it has no charge. So I'm going to create a particle called a neutron. He didn't do any tests, and he didn't do any kind of experiments, and Chadwick discovered the neutron purely based off of mathematics, which is a really cool discovery. Now later on, other scientists came along and said, hey, Chadwick was totally right. The neutron does exist, and they did confirm it with experiments. But it was kind of neat how Chadwick discovered the neutron initially based off of math. And then later on, there was a guy named Niels Bohr, and he said that, hey, there are electrons on the outside. There are protons and neutrons in the center, and the electrons are in the outside, but more importantly, the electrons are in different levels. So here's the first level, the second level, and then the third level. And they're in all these different levels, or shells, he called them. So he said like the first shell, the second shell, and the third shell. Everyone else just kind of thought like electrons are just randomly out there, all mixing together. And Niels Bohr kind of said like, no, they're definitely in these shells. And he had a big experiment as well, where he energized these electrons and they shone back different light spectrums at him whenever they reached a different energy level, but it's a little bit more complex. Okay. Now, so just to recap a few of these things, what kind of electrical charge does a proton have? It's positive. The neutron, it's neutral charge, and the electron has a negative charge. Now, where is it located? Well, thanks to Rutherford, we now know the proton is located in the nucleus, as well as the neutron. These are the hard, dense things that were in the center of the atom that the alpha particles would bounce off of. And those electrons were on the outside. Okay. Now, the next big question is, what is the atom mostly made up of? Well, it was mostly made up of empty space. In the terms of like 99.9% nothing. And I'm not meaning like air or like nothing. There's no particles. There's nothing there. Okay. So we always draw pictures of like atoms, but this should be the true size of an atom. So here's our picture of an atom. It's roughly about this size right here. And this is roughly about the true size. If an atom was this big, like this circle I drew, the true nucleus is about this size, right? And those electrons are very, very small. So when I say like it's 99.9% nothing, in actuality it's more like 99.999% nothing, empty space. And the nucleus is a very tiny object. And so when Rutherford was doing his experiment, the only times he was shooting millions and millions and millions of alpha particles at it, and most of these alpha particles would just go right through. The only ones that bounced off of it were the ones that hit this tiny little nucleus right in the center, okay, which was not a very large target. And that's why most of the alpha particles went straight through the gold foil. Only the very odd one that hit the nucleus bounced off of it. But Rutherford ended up shooting hundreds of thousands of alpha particles at this gold foil, and some of them were able to hit that nucleus and bounce off. And that's how he discovered the proton.